Great. Hello, welcome to a special remote ENGI 2203 lecture. So I'm going to take you through how EEPROM works, and this can be used to actually store data on your microcontroller, because what you might need to do is you might need to store something like if you're trying to implement the pin code, and you want that to persist between resets, this is a feature you're going to need. So this is something that's really handy to do, and what you'll find is it's not that difficult to get started with. So I'm going to talk about what EEPROM is, and I'm also going to talk about how we use it in practice. Okay, so when we say EEPROM, you'll see a lot of names for this. So people might call it E squared prom, which is really a fancy way of having two E's in a row. So like we're multiplying them together, so we make it E squared. And EEPROM is really what we're talking about, and this is electrically erasable, programmable, read-only memory, right? So we have these three things involved in it: the electronically erasable, programmable, read-only memory. So there's a lot packed in there, and I'm just going to really quickly take you through where did all this come from. So the beginning is what we call read-only memory. So read-only memory can't be written during runtime. What this really is done is this is kind of the origin of like a lot of old video games and stuff would use this type of memory, old computers obviously. But what you have is if you're mass producing something, you actually make a memory that's defined at manufacture time. And so you define it at manufacture time. So here's the chip, and this is like part of the chip. And you can sort of see maybe, there's some like different patterns here. And what you're actually seeing is patterns of ones and zeros. So each of these rows is going to hold a certain number of bits, and each of the bits is going to be either a 1 or a 0. And so to write data, you actually have to produce the device. If you're making millions of devices, that's okay. But if you're making a small number of devices, this isn't so handy. So what we have next is programmable read-only memory. So now we're adding in the fact that we can change the programming of it. How this works is normally there's a few ways to do it, but the most common is some sort of fuse, they call it. And so this is literally, so in this example here, if you remember your matrix keypad, this is actually very similar. We have a matrix where we have rows and columns. Interconnecting them is something. So here it's shown as a link. Often it's like a little diode. But if we want to program a bit, we actually blow that up. So we pass a high current through that link, and that link gets destroyed. And later, if you try to scan it, you'll see that there's no connectivity. So you either have a connectivity like here, could read as a 1 or a 0, or an open. So normally what we have is historically this would be a 1, I believe, and this would be a 0. But there's different sort of fuse patterns and stuff like that that you could use. Okay, so this is fine. We can only program it once. What if we want to erase it? So now we get into erasable PROM or EEPROM. And this is something that you saw a lot of over time. It's not used really anymore now. You might still run across it though, especially if you're repairing any old devices. This is very easy to identify because if it's a classic EEPROM, there's a window on the device, and this just isn't so you can just look at it and admire the chip. What this actually is doing is the way we program it is no longer this destructive sequence. Instead, it's programmed in a way that we can actually erase it with UV light. And so this window, you expose the chip to UV light. So you typically put it in an eraser for like 5 to 20 minutes or more, depending how strong the eraser is. And this actually resets everything back to the default state, which is actually normally all ones. And so what this means is that, the manufacturer can program it during the programming cycle, but they can then update it. So it's not super fast. A long time ago, if you were doing development on this, this is a huge hassle, because you think about your nice little Arduino that you can reprogram in a few seconds. Well, imagine if every code change took 20 minutes just to erase the device so you could try a new code version, right? So every time you need to change it, you need to erase it. So you either had to then have multiple of them, so you'd have people with stacks of these chips doing development, or you needed a really fancy emulator, it was called, which let you avoid this this erasing step. But that's kind of the origin of this stuff. So what you don't have to deal with any of that, luckily, because nowadays you almost always are going to be using electrically erasable PROM. So now that erase step is done electronically. This example here, by the way, so these are all standalone devices that serve one purpose and one purpose only, which is to be an EEPROM chip in this case. So it's just a chip that only gives you some amount of storage. These devices all work pretty similar now. There's different ways of implementing it. This figure here, by the way, so this is a really tiny cross section of the device. So if you look back here, if you take this chip, you slice it, and then you look at the side of it, and you zoom way in. This is just going to be a tiny portion of it. To store 1 bit, we use this floating gate system. And basically what you have is this that seems to just be floating in air is actually isolated with dielectric. And if we can put a charge on this gate, it actually kind of stays, it'll stay in that charge state or discharge state. So we have a way of actually changing the charge on the floating gate is how we store data. And now to do this, there's a big caveat here, right? You'll notice this thing says 12 volt here. And this is actually the case. So to program these devices, we needed pretty high voltages. So with standalone programmers, so these devices used to go in a standalone programmer, that you'd put the chip in and it would put 12 volts on the pin as needed. You only needed that during programming, not during use. And it would go do this, changing the state of the floating gate. Nowadays, that's not really typically needed. The 12 volts is still there, or it might not be 12 volts, but a higher voltage. But what happens is we have what's called a charge pump. So inside the device, there's some way that it generates this voltage. You don't need this crazy external power source. So in your specific device, so the ATMega328P, you can pull up the data sheet, and what you'll see is that it talks about having EEPROM, so it says 1 kilobytes of EEPROM, as well as some other memory types. So you are given inside that device a certain amount of this electronically erasable programmable read-only memory. You might ask, you might say, well, actually, what are these other memory types? SRAM and self-programmable flash. That sounds like something we can program. Yeah, and it's true, you can. So the first thing I'll scratch off the list is SRAM. So SRAM, static RAM, it loses its state. So once you power this device down, it's going to lose its state. So if you try to store the pin in a variable, as soon as you remove power from the device, it's going to die. So you can, in fact, try some, interesting stuff like keeping the device powered with a capacitor or something like that. But really what you should be using is one of these other memory types. Now, what about flash memory, right? There was also flash memory here. And actually flash memory, so you're not wrong if you think that that's an option, because flash memory and EEPROM are actually the same thing. So they get different names, but how it stores data is still the same sort of idea of here. What's actually different is how it's organized, and so how it's designed to be used, right? So even though it's the same thing, it's designed differently. Flash memory, you typically always have to work on what are called pages, which is a certain sequence of bytes. So you always have to write, and this could be like 1024 bytes or some large amount. It depends on the device. It's typically 512, 1024, something like that. But what this means is that you always erase and write that same chunk at the the time. You can read an individual byte, but if you want to update, so let's say you have this 1024 bytes here, right? So we have a whole bunch of bytes in one page. And if you're just trying to store a pin code that's 4 bytes long, you actually have to read this entire section, store it somewhere temporarily, update the pin code. You erase the entire section. There's no choice but to erase this entire block of memory here. You have no way to do it just on a smaller block. And then you copy this back. So it's kind of annoying to work with, is the gist of it. So if you're just trying to store small amounts of data, you don't want to use Flash normally, because you'll have to do this issue where you end up erasing the whole thing to update it. EEPROM normally is designed to allow byte level optimizations or operations, sorry. The other thing you've got is the sequences might be optimized for the EEPROM memory. So even though it's the same, design and same idea, there's going to be differences in what are the distances here, what is the size of these gates and stuff like that. There might be differences in where it is on the chip, other things like that. And this will affect the number of cycles that the device can actually be written and erased by. So these actually have a finite number of cycles. You can't do it forever, so you can't just continuously erase and rewrite the data. You run into this actually, so as a sort of a side note, flash SSDs, so in computer hard drives, the SSDs, they have this issue too. So they do something called wear leveling, where the data is actually getting moved around on the device to deal with the fact that certain cells are basically going to be destroyed over time by reuse. So they have a lot of algorithms to do that, and it hides it all from you. So when you buy a flash memory device, it actually has more space in it than it claims, because a lot of it's reserved for basically remapping. So a lot of it's reserved to remap when certain cells die. You have new cells that take their place. So that's sort of the difference here. So in our case, we're just looking at EEPROM. It guarantees 100,000 erase write cycles. Probably it's more than that though. So don't worry about killing your device, because this is guaranteed, remember, over the entire temperature range. If you look at the data sheet, I don't know offhand, but it's probably something like minus 20C to 85C that it's guaranteed to work at. And a lot of this stuff gets worse, at higher temperatures. So if you're running this at just room temperature, it's going to last a lot longer. Okay, so we talked about Flash versus EEPROM. So how do you use EEPROM? Okay, so we talked about what it is really quickly. What you want to do is you want to read some bytes from EEPROM, and you want to write some bytes from EEPROM. It's actually pretty easy. So AVR libc, which is our library here, has this link that gives you, if you include this avr/eeprom.h, it's going to give you some functions that deal with the EEPROM for you. The only trick you really have to watch out for, right, is that we're passing in what they're calling a pointer, this __p. This is just an address in the actual EEPROM itself. So if we look back at our data sheet, right, we have 1024 bytes of EEPROM. Get rid of that. Come on. And there we go. We have 1024 bytes of EEPROM. So this means we're just going to address it, and the EEPROM address starts at 0. So basically you just need to record where you wrote stuff in this address range. So I'll give you a little example of using that in a second here. The other thing I'm going to show you or going to mention is there's a really nice tutorial. Dean Camera has this tutorial. The original version is on the AVR Freaks forum, and he's got an updated PDF that I also I linked there, and that PDF is uploaded to Brightspace as well. So if you want the EEPROM tutorial, you can just check. It should be just under this the lecture slides for this guy here. Yeah, so really all we're going to do, and watch out on the tutorial here. So there's some kind of, because this is some old form stuff, there's been a few mistakes. I don't know. If you use the PDF, it includes it, but basically this is just supposed to say include this file here. So I'm just going to take, what I'm going to do here is I'm going to do a demo. And I've just got like a UART application up. So if we say end session here, right? I'm just going to build this. And all I've done is I just have the Arduino on a board. So I don't have anything plugged in with it. So it's just plugged in like that. Okay. So we'll download it. And again, I've just saved a UART settings one, as I talked about before, so you can just double click on that to connect. And all that's going to happen is if I press this reset button on it, you'll see it prints the hello world. So there you go. So that's all we got. What I'm going to do is I'm just going to make a simple application that reads from EEPROM and writes to EEPROM on user request. So for example, let's say I have my little pin code here, right? So I have this pin code variable and I want to load, from EEPROM. So we're going to go up to the top. And in our includes here, we're going to say include avr/eeprom.h. Easy. And we're going to print, what's going on here? I think I hit F11 or something when I was trying to page up, so let's ignore that. Okay, we're going to print the value that's in that pin code variable. So if we said, for example, we'll just printf, I'm just going to kind of cheat here. Yeah, let's print it in hex, just so it's a consistent width. And I'm just going to print each of those in sequence. Right, so all I've done is I've printed the value here. Now the issue is this is just going to be garbage, right? It might be 0, it might be something else, because I haven't actually loaded the value. And you know what we want to do is, if we get a character, we're going to say, you know, let's get a. So let's actually make these decimal. Sorry. We're going to get a number, and we're just going to write it in to the pin. Okay. And remember, we always need to pass a pointer here. And this is going to expect an integer, actually. So what I'm going to do is I'm going to make a new variable called int input. Right, and I'm just going to get one input at a time, like that. And because it's scanf, I print this. So normally, obviously, I'm using scanf here. The idea is you'd be using your number pad or something. So you don't have to do this complexity. I'm just trying to show you a way of getting these numbers out of here. I smaller than 4. I plus plus. So all I want to do is be able to read in this pin variable here. So let's do that. And we'll say pin I equals input. Right, so all I've done, make this a little bigger, is I have my variable. I don't initialize it, so the compiler might complain about that, but I print the value out, and then afterwards the user can enter in a value 4 times in a row. And we could say, for example, like, okay, pin written to, and we could just print what this is. And there we go. Okay. So you can see all I've done is I've made a little simple input-output sort of function. So just disconnect. Close session. So again, all this code does, printf, this pin, so this is just a variable that's 4 bytes long. So I'm trying to show you, something using an array, because I assume you might want that as well. I then take the input from the user. This would be your pin code really here, not scanf. And then I'm going to print it back to the user. So what we want to do is we want to actually write this to EEPROM afterwards. But, it's always good to start simple. And that's exactly what we're going to do here. So what you notice, right, is if I reset this device, so all I'm going to do is I'm, again, going to use the reset button right now. So when I reset that device, it's coming up with some default. So what's happened is this device is just got garbage in the memory. So this is whatever was in the SRAM. It's not guaranteed to be the same. If we power cycle it, it might come up differently. So let's actually do that. So if you remember here, right, so it was coming up as 177, 176, and I'm just going to unplug this and replug it, and we're going to reconnect to PuTTY. And in that case, it actually did come up as the same, but it's not necessarily guaranteed to. Okay, so I should, in theory, now be able to enter some numbers in a row. Right, and then it says OK, pin written to this, and there was no new line after. That's the only reason it looks kind of messy there, but you can see it did accept the pin. Now, what I'm going to do is I'm just going to reset this device, and we'll see what happens. Right, and it's now gone back to the original. So in that case, what's happened is I was hoping maybe it kept the memory around, but it's reinitialized the memory somewhere else, and it just put garbage in here. Okay, so we know this could work. We just need to actually save it. So now all we're going to do is we're going to use, so using this tutorial, you can see there's some various functions, like there's EEPROM read byte. What we're probably interested in is there's like a read block function, and this will read a series of bytes from the EEPROM at once. So the only kind of trick with it, so if we take that function here, right, let's read from the EEPROM. So pointer RAM is where in RAM we want to write it, and this has to be a pointer, okay? Pointer EEPROM, this is just an EEPROM address, so we could start at 0 if you want. And the final thing is how many bytes, so 4 bytes I'm going to say. Now we'll see this might actually complain because normally these should be pointers, and these aren't really going to be interpreted necessarily as pointers. So you can force it if you say this, like const void. If it's complaining, you might want to do that to tell it that no, these are supposed to be pointers. It depends a little bit. Oops. So it actually didn't expect const because it's not expecting a constant. So void. So in case you get warnings, you might want to do that to satisfy the compiler. So let's just again close this. Download, run PuTTY. Okay, so now we're getting 255, 255, 255. What's going on here is that if you kind of remember back to what I was talking about, one thing I mentioned is that when this gets erased, it always erases to a 1. So it erases to a 1 state, which is the same as kind of old school EEPROM as well. So this erases to a 1 state, and we program it down to a 0 state. So if it's erased, it's already in a 1 state, and we're going to program it down to 0. So that's where we're getting 255, 255, 255 here, because 255 is hex FF, which is all 1s. Okay, so what we want to be able to do is we actually need to be able to write to memory. So let's look up here. There's an update block function, and this will do our write. So if we say take to EEPROM address dest from source, so we always want to check, okay, the dest will be the second one. So we can just do something like this. We can just say EEPROM update block, and it should deal with everything for us. So we can see this is expecting a pointer type, so let's keep it happy. The pin, the destination. I just started at address 0 and 4 bytes. So if this works, this little function here is going to do the expected void. This isn't supposed to be const. There we go. This should just give us a nice little EEPROM rate. So if this works, I can now put in a pin. So it's going to run once with the old pin. So I'll put in 12, 55, 66, 99. So it says, okay, pin written. If we reset the device, the moment of truth here is, there we go. So it's read from EEPROM what the pin value was. And this is going to be the same. So if I take this guy and unplug it, plug it back in, Putty's going to complain. And we say that's fine. Restart session. You can see it's stored them into EEPROM itself. So using EEPROM is really easy. All you need to do is call these functions. I'm using a block. You can use a byte. You can use a like 16-bit or 32-bit word. So there's different functions that help you use specific. So there's 16-bit, for example, different data types. So just check the data type you need in case you need something that's not just a block. I should mention there is a nice, so if we go to Dean's website, he's going to give you a really good way to do this. It just downloaded here, but I'm just going to show you GitHub. Because there's kind of an even cooler way to do it, which, I just leave as a aside. And he mentions it in the tutorial that you can actually define a special type of memory and this EEMEM attribute. So you can actually use this attribute, and it just automatically deals with the access for you. So you need to do a little bit of working. So the only thing is you can't just necessarily deal with all the stuff like you want, but you may find it easier to more explicitly deal with them that way. But I leave that up to you to think about where you want to go with this. But the basic idea of using these EEPROM read block and EEPROM update block is basically all you need. Just watch out. So a little caveat here I'm going to give you. I used address 0 here. That's actually not a great idea to do. You might say, why, what's wrong with address 0? It starts at 0, goes to 1024. That's within the range. There is some potential for reliability issues. So there's been kind of over the years some findings that suggest if the device powers down, so one of the problems with EEPROM and, the actual, if you look at the ATMega datasheet, I just totally glossed over this. Just open the datasheet here. It's going to talk a lot about, so it talks about sequences. You don't have to worry about the sequences because we did that with our little macros. But there's a bunch of stuff about preventing EEPROM corruption, which can occur if the voltages are too low. I mentioned before about how there's this high voltage is needed. So actually, the EEPROM can be pretty sensitive to out of voltage condition where it can't generate internally the required voltage. So one thing that can happen is that let's just use this, that EEPROM space, because it's all here, address 0, sometimes people avoid using it because if the device is powering down, so if you say you were trying to write to this address up here, say at address 87, what can happen is that if this starts to get corrupted, it's possible this pointer points to the wrong location because of the falling voltage, and you end up overwriting address 0. It would also be the case that, if you screw up the function call, some indexing, it's very likely you're going to end up writing to address 0. So you will see in code, so this is the EEPROM address, by the way, sorry. Very often that people start at some offsets. They start at whatever you want, say 32 or some other offset that's not 0. You probably don't really have to worry about that, but it's it's good to keep in mind when you're choosing it. And again, I've just chosen 0, so you could say I'm going to rate it address 12 or anything like that. If you're writing multiple variables, just be careful you don't overlap, right? So what I would need to also do is, let's say I want to do EEPROM update byte, right? So say I had a single byte that I wanted to update, and I might say like, okay, where am I going to store this? I'm going to store this at address 13, and I'm going to store value 67 there. But remember, right, that's going to overwrite our pin because our pin starts at address 12 and uses 12, 13, 14, 15. So we would want to start at address 16 here. So just keep an eye out for stuff like that. So you can get, you can easily overwrite different values if you're not tracking all this stuff correctly. But yeah, that's just a quick overview for how you use EEPROM. Hopefully you find that useful. As I said, it's really straightforward if you just use those functions to update and to read. That will kind of work just as I showed here. And for more information, Dean Cameron's tutorial goes into a lot of detail on this.